Actually, visually, you can And if the time allows, I'm going to touch upon the EFT of black hole perturbations. Okay, that's maybe is being active research right now. Okay, and these are the reference I'm following for these lectures. The first one is from Marco Cellone, that's the notes on QFT. The second one is Leonardo Senatore lecture on inflations, and the last one here is the original paper on EFT of inflation that you can check it using these archive numbers, and perhaps there are many more references I will give you along the lectures. Okay, right. So let me first start with the first lecture, the basic concept of the EFT. Okay. Okay. So yeah. So well, actually the idea of the EFTs start from the fact that the universe comes with the scales, that you have many scale in our universe. Okay, so the first lecture is going to be, well, basic concept of EFT. Okay, and all the thing comes with the fact that our universe have many different scales. Okay, so the fact that the black. Yeah, thank you. Uh, our universe contains several scales. Okay, contain several scale. And for example, if you draw the energy scales like something like this, okay, and this is the energy scales, and the highest scale you can think of is M Planck, that's around 10 to the 19 GeV, right? And probably this is the highest energy scale that our theory, that our understanding worked so far up to this scale. And beyond this scale, who knows, that maybe you need a quantum gravity or something beyond GR and all that. Okay, so this GeV. And below Planck scale, maybe you can think of the inflation, the scale of inflation, which is around 10 to the 15 GeV. And but inflation is now it's just a like kind of hypothetical models, and we have not directly detected the scale of inflation yet. Okay, so there's a scale of inflation that is around 10 to the 15 GeV. Maybe in a couple of, I don't know, maybe 5 years now from now, that suppose we have detected the primordial Gaussian wave, the B modes, maybe that thing would tell us the energy scale of inflation, okay, the detection of B mode, detection of B mode. And B mode is some kind of the primordial gravitational wave coming from the early universe. And this detection is going to to help us identifying the energy scale of inflation. And if you come further down, you are going to reach the scale of electroweak scale, that is around the mass of the Higgs boson and the mass of the W boson. Okay, that is around 100 GeV each. Okay, the mass of the Higgs is 125, and the mass of W is like 100 GeV. Okay, so in this scale, we know that the standard model of particle physics works really well. So you can use the standard model to calculate the scattering amplitude, to calculate the cross section, and all that. Okay, so here we know that in this scale, the standard model of particle physics works really well. That maybe you have heard of SU3. The gauge group of the standard model is SU3 color times SU2 left, and then times U1 hypercharge. Okay. You can use this theory to describe physics at these scales. And of course, one has to break this electroweak sector to get the U1 electromagnetic that we know of, and then to generate the mass of the elementary particles through the Higgs mechanism. Okay. So perhaps in how to break this symmetry, I will touch upon in my second lecture. Okay. And then if you go further down, you are going to reach the mass of like the neutrino, that is around 1 eV. Okay, the mass of neutrino, and this is really far from the mass of the Higgs or the mass of the W boson. Okay, around 1 eV. But then if you go even further down, you go to the scale of lambda. I hope you guys see this thing. Lambda is a cosmological constant. That is a kind of vacuum energy. The cosmological constant. Constant. And this is around 10 to the minus 4 eV. Okay. Minus 4 eV. And even further down, if you go to even lower, you are going to reach the scale of the Hubble at the present time. And the scale of the Hubble H0 here is around 10 to the minus 33 eV. So it's very further low. So yeah, the scaling is not good. Minus 33 eV. So in terms of the length scale, so this is going to be super large scale. Okay, so that this corresponding the energy scale. So you see that our universe here contains a lot of scales that starting from the highest scale in Planck down to the Hubble today. And actually the ultimate goal of us, like physics, is to have the a single description that we could describe physics all this scale at once. But in reality, what happened is that we cannot. I think it's really it's more convenient to isolate our other physics that are not irrelevant to what we are interested in. Okay, so the idea of the EFT is that you are going to isolate other physics that you are not interested in. Okay, going to isolate out others physics that are not relevant to your to the scale you are interested in. Irrelevant to the scale you are interested in. For example, if I'm interested in the physics of the large scale here, so what I'm going to think of is, of course, the first thing is gravity. Suppose I'm going to, if I'm focused on the physics on large scale here, super low energy, so what I'm going to think of is the gravity. That's the first thing you have to think of, okay? Gravity. And you may focus about those electroweak forces or the strong forces, okay? And on top of gravity, you may have other additional forces that you could have, maybe coming from the scalar field or vector field or other tensor fields that you can think of. Okay, so I left this as a phi. Okay, that could be other fields that you can think of. Okay. And perhaps in the last lectures in this school, you have seen the skeleton theory, like a Hondensky theory, Dawes theory, whatever. And so that is one example of the effective field theory. Okay. Right. Let me erase this. Okay. Actually, so far, what you have seen from the like in the last couple of lectures, the skeleton theories and Kearson theory, Kondensky theory, and those things. Actually, we are going to look at those things, but from the different angle. Okay, but from different angle. So what I'm going to show you, maybe you're gonna. I hope you will see at the end of my lecture that. So the goal is to show you that the EFT of inflation or dark energy that we are going to formulate in the couple of lectures, the EFT of cosmological perturbation that we are going to formulate. So this EFT, I wanted you to see that it unifies. Okay. It unifies all the effects of the skeleton theories of skeleton theory into a set of finite parameters. Set of finite parameters. Okay, so you're going to see that this EFT of inflation or dark energy, okay, that we are going to write down contains a finite set of parameters, and each parameter corresponds to those theories that you have seen before. Okay, like a K-essence or Hondensky or beyond Hondensky or Dawes theory or even beyond that. Okay. And in this way, we can describe physics in the universal way. Okay, kind of we unify all this effect into a finite set of parameters. Okay, so I hope at the end of my lectures, for 4 or 5 lectures, you are going to see this statement. Okay, right. Right. So let me first start with the simplest example that you can think of the effective field theory that perhaps you have seen in your electromagnetic course in your undergrad lectures. Okay. So that example is the multiple expansion. It's very easy. Okay. So it's a multiple expansion. Multiple expansion in electrostatic. Okay, it's very easy, and you can understand some terminology of the EFT using this example. Not all, but some terminology. Okay, in electrostatic. So what happens is that suppose you have the charge distribution. Okay, some blob here, and you know rho, which is the charge density that depends on the location of the source. Like this, and what you want to know is you pin down some point in space here, point P, and you wanted to know the electric potential of this. Okay, so you want to write down, you want to calculate this V as a function of X, like this. Okay, and this is really simplest example that you have seen this before. Okay, and for this blob, for this row, we have the typical scale or typical size for the source of the charge distribution. So let's define R as the typical size, of charge distribution of the source. Okay, and of course, you can go on and use your Griffith book or whatever to compute V in terms of rho, right? And the result is the following: that Okay. So result is the following, that you have the potential is the integral of d3x prime, and then you integrate rho x prime divided by x minus x prime. Something like this. I hope I didn't miss anything. Yes. Well, there are some factors like 1 over 4 pi epsilon. Yes. Which I usually. Okay. Right. So from here, yeah, you can go on, and suppose you know rho, the charge density of this blob, then you can go on and compute this. Perhaps you can do it analytically, or you can use your computer to calculate this electric potential. But we can do better than this. Okay. Suppose if you go on and doing the so-called multiple expansion, so you're going to expand this 1 over x minus x prime. X prime is the location of the source, and the result is the following. So if you suppose that r, which is the side of the distance from the source to the point you are interested in, is larger than the typical side of the blob, so you can write down v as on the basis of the spherical harmonic function. Okay, so you're gonna be summing. This I have to look at. Okay, good. 1 over. Okay. Okay, now you have this multiple expansion that when r, this small r is larger than the typical size of the blob, then you can do the expansion and then write down your electric potential in terms of this spherical harmonic function. Okay, and QLM is a coefficient of this YLM. Okay, actually, suppose that and this QLM is given by rho, right? Suppose that L and M is 0, so you can just integrate rho over this d3x prime. But then the idea of the EFT comes when suppose that I wanted you to guess the form of this without knowing the exact formula of the electric potential. Okay, so the idea is that suppose that R is super large. This small r is very large compared to the size of the object, and I wanted you to guess, okay, to guess the form of electric potential without. Suppose you don't know about this formula of the electric potential, okay? So how can we guess about that? Okay. So the first approximation that we can guess is that suppose that this r is super large compared to this capital R, then this blob can be considered as the point charge. Okay. Then once this guy is a point charge, then basically you can use the Coulomb potential to approximate that thing, right? So you can write down the first term as the I have to look at the coefficient. Okay, good. 1 over 4 pi epsilon r 0, and then q over r. So this is coming from the fact that you do when r, the small r here, is larger than the typical super large compared to the typical size of the blob, then you can just approximate this as the point charge. And then the first term is just the Coulomb potential. And the first term is nothing but the monopole term for this guy. Okay. So monopole is when you set L and M to 0. Okay. So this is called the monopole. Plus, there are corrections coming from other terms like a dipole term. So let me just write down dipole term, okay, which is like a pi ni divided by r squared. So this is a dipole term, okay, and p is a dipole. this, and the dipole is the product of the charge times the distance. Okay, and you can add other terms like quadrupole terms. That means Qij, Ni, Nj, something like this. Sorry, Ni is defined as is the unit vector divided by, yeah, it's a unit vector. Cube. Okay, and so on. So the more you add, the more accurate you can describe your electric potential in this case, right? And this is a quadrupole. Okay, but the point is that those high order terms will be suppressed by the capital R divided by the small r. So we have the expansion parameter, which is epsilon, which is r divided by the small r. Okay, the more you go, the more the terms are suppressed compared to the first three terms. Okay, and this is our expansion of the expansion parameter in the EFT. So in other words, here the epsilon plays the role of the organized, how you organize the term in the EFT. Okay, so this epsilon we call this as the expansion parameters, and it's organized how you write down the terms in the effective field theory. Okay. Expansion parameters. In other words, actually this epsilon controls the so-called derivative expansion. Okay, so it's 1 over r expansion. Or, yeah, derivative expansion. Expansion. Okay. Right. So yeah, I wanted to, yeah, when you go to very large distance, mean you go to low energy, and those terms that are not important at low energy is called irrelevant operators. So this is kind of a language of the EFT. So let me just write down terms that are not important at low energy or large distance at low energy. So we are going to learn these terminologies along the way. Okay, at low energy is this term is called irrelevant operators. Okay. Okay, good. Right. So in this sense, when you write down this, suppose you don't know about the exact formula of this integral formula, and you just write down this straight, and then you see that there are some parameters appearing, like a Q, Pi here, and the Qij, and these are the EFT coefficients. Okay, so this kind of the charge, the dipole, and the quadrupole here is the EFT coefficients. EFT or parameters. And the thing is that there are two ways to determine these parameters. The first way, of course, if you know the exact formula from this integral formula, then you can determine by using the matching condition between this EFT language and the exact formula. So you can write down Q in terms of the rho. So you know how these parameters depends on rho, on the details, the microscopic detail of the object. Okay, but suppose you don't know about this formula, then you can go on and do some measurement. So you can determine these EFT parameters by using some observations. So there are two ways, sort of. Okay. Okay, so I have to look at note. Yeah, so essentially what we are having now is that. Okay. So the thing is that when R, the distance that you are interested in is larger than the typical size of the blob, you are essentially in the regime of the low energy physics here. R is larger than the capital R here. So it's okay, it's okay. So yeah, so in this regime, you are in the so-called the low energy physics or large distance, okay, low energy regime. Or sometimes we call this IR regime. Okay. So now we are going to use some EFT language. Okay, IR regime. IR is coming from the infrared. Infrared regime. And in this regime, the EFT that you just write down there works. Okay. So this is the regime of the EFT. EFT works. The EFT holds. And of course, you can imagine that if the distance r is getting smaller and smaller and compatible to the size of the objects, then the thing that you just write down there just breaks down. Okay, then you need the UV completion for that. So in this regime, when r is maybe less than or just compatible to the size of the object, you are in the regime of the UV regime. And UV is coming from the ultraviolet. Okay. Ultraviolet. Violet. Okay. And in this case, you need the UV completion to describe physics at this scale. Okay. It's called UV completion. Okay. So in this sense, the EFT that you just write down here as the small r is getting smaller and smaller compared to the size of the blob of the capital R, then you just have to stop using this thing and then you back to the exact formula that you have, and then now you have to compute this integral exactly. So you cannot use this EFT expression. Okay. And well, you know that if you do the matching between this EFT and the exact formula, you get the formula for Q for the dipole and the quadrupole and so on. So let me just write down. So like for example, P basically. Okay, so the dipole is just well, if you estimate this, it's going to be like a charge times the distance. Okay, Q times xi, more or less, because the integral of d3x and rho is like q, and then times the distance, and the quadrupole is. I'm sure you have seen this before. Yeah, and this quadrupole is just proportional to the charge times xi, xj, something like that. Good. What else? Okay. So the idea of now now you can see that you can study the EFT in two ways. Okay, in two ways. The first way is the so-called bottom-up approach. Okay, and the second way is the top-down approach. Let me just write down. Okay. So now in this example, you see that the way to study EFT, there are two ways to do that. One is the bottom-up approach. And in this bottom-up approach, if you suppose you don't know about the UV completion, you can just simply write down all the terms that describe physics of your interest, okay, in your scales. Okay. So the first one is the bottom-up approach. Bottom-up approach. So that means you just go on and write down all the terms that are compatible with your, well, so far I have not talked about symmetry yet. So just write down all the terms that are compatible with your derivative expansions, and then you don't know about the UV completion. You don't know whether the theory at high energies, you don't know about these. You just write down all the terms that you can write down and describe physics at this scale, and that's it. Okay. So bottom-up approach. Okay. And the second one is top-down approach. Okay. Top-down. Approach. And in this case, the thing is, in this top-down approach, suppose you know some UV completion. Yeah, you know UV completion, and you integrate some heavy field out, and then you are going to obtain the IR theories. Okay, so in this case, you in our EFT language, we integrate to obtain the EFT, or the IR physics, IR theories. So what you have to do is we have to integrate out. So I put the word integrate out in the quotation. Integrate out, because we are going to investigate what it means by integrate out. I assume that often. Okay. Get out heavy modes. Okay. Right. So we are going to explore this top-down approach using this integrating out approach. Okay. Right. I will show you how to integrate out the heavy modes. Okay. And then you get the IR theory of the light mode. Okay. Right.
So in this case, you know UV completion, right?
Exactly. So in this case, the UV completion is known. It could be partial UV completion as well. It shouldn't be complete UV completion. No, yeah. Well, by UV completion in the language of the QFT is that the theory should be renormalizable. But okay, I will talk about it later. Yeah, in some sense, if you want the fact that we call this UV theory or UV completion is that that theory, it should be renormalizable. So it shouldn't contain the observer shouldn't contain any infinities. Okay, so this means it should be the theory should be renormalizable. Okay, so we have some example for this. I will show you later. Let me erase this. Right. Good. Okay. Right. So what else? Okay. And okay. If you have any question, just ask me. Okay. Yeah.
Like, why do we need only like UV completion? On the other hand, if I want to obtain the efficiency of UV theory, do we need to have like the IR completion?
No, yeah. So the thing is that to describe physics at low energy, there are two ways. So the first thing is that you can just write down all the terms that are compatible with your derivative expansion in the. Sorry, let me just write down. So in this case, yeah, R here, the capital R is here, and this is the EFT regimes. So yeah, so the first approach is that you just write down the EFT here, all the terms that compatible with the derivative expansion, the epsilon thing. So epsilon is R over big R and should be less than 1. You just write down all the terms in this regime compatible with this derivative expansion. But actually, there should be more principle here. It's not just derivative expansion, but also we control with the symmetries and so on that I have not talked about yet. Okay, and also, okay, let me mention that since you ask, not on top of the this derivative expansion that controls by this epsilon, we also have normally we also have symmetries in the EFT. Okay, symmetries in the EFT. For example, that in the multiple expansion, if you impose the spherical symmetry, for example, then what you can write down is just the first term, the monopole term, right? You're not allowed to write down the quadrupole or dipole terms because it breaks spherical symmetry. Okay, so if you impose the spherical symmetry to that multiple expansion, you just Q over R, just a Coulomb potential. Okay, and yeah, so you add this symmetry as some how to say, like a selection rules to your EFT. Okay, and also you have to specify how many degree of freedom you have in your EFT. Okay, the number of degree of freedom you have. Like let's say that in the scalar tensor theories, usually we have 3 physical degree of freedoms. So we specify that our EFT should contain 3 degree of freedom, 3 physical degree of freedoms. Okay, that should be the healthy kind of thing. Okay. Yep, and we will touch upon this later. Okay, and but this is the bottom-up approach. Okay, you just write down all terms compatible with these principles. But there's also another approach, which is top-down approach, that you start from the UV completion here, and then you integrate out. I will tell you later what it is. You integrate out the heavy guys, and then you arrive at the low energy theory. Okay, right. But these days there are some ongoing research, like because usually we assume that in the UV theory, in UV completion, this UV theory contains or has some nice properties. For example, locality, causality, or Lorentz invariance. And this principle of the UV theories can impose the bounds on the EFT parameters. So, but that's going to be another story. Okay. So yeah, some property of the UVs can place the bounds on the EFT parameters. Properties. Put the bound on this. Okay, and if you want this, go to the programs called positivity bounds that people use to put the bound on the EFT parameters using the properties, nice property of the UV physics. Okay. Through the so-called like scattering amplitudes or whatever. Yep. Okay, but there are a lot of subtleties here. Okay, if you break Lorentz in the IR, we come to that. If you have gravity, then things become messy and all. Okay. Now let me study another example, but now we move to the field theory language. Okay, we just jump from the multiple expansion in electrostatic to the field theory case. Okay, so in this case, we are going to study the two field model. Okay, two field model, two scalar field model. Two field. Okay. So in this model, you're having two fields. One is light and one is heavy. Okay. So let me just write out the model, and then we can discuss later. Okay. So the model is the following. First, let me just write down the UV completion of this theory that describes the physics at high energy. Okay, so it contains two fields. One is the heavy, one is light. Okay. So in this model, you have two fields. One is phi chi, and then the other is a chi. Okay, chi is let's take m. The capital M here is which the mass of the chi is larger than the mass of the phi. Or you can even do better. You can take this small m to 0, but fine. You can take this phi to be massless. But, yeah, and so these two field couples through this interaction, the cubic interaction. Okay, and G is a coupling of this interaction, and this theory is we just write out in the Minkowski. Okay, it's in Minkowski. And it's a UV complete in the sense that this model is renormalizable. So yeah, when you compute loop diagram or whatever, it's finite. Or you can do renormalization program thing. Okay, and yeah. So for example, chi here. Suppose I write down the vertex, the vertex for this. This is chi, and then this is phi, and the coupling is the G. Here. And if we impose the fact that this theory remains weakly coupled all the way, that means this coupling G has to be less than unity. But be careful that this G here contains dimensions. Because chi here is scalar field, and this is also scalar field. So 1, 2, 3, and this guy contains scale of dimension, energy 1. Okay. So actually, you have to be careful whether when you require the theory to be really coupled, you have to compare this G here with some energy scale you are interested in. Okay. Anyway, so this theory is UV complete.
Is there any particular reason why we consider cubic interaction?
Oh no, this is the example that to show you how to integrate out the heavy guy. That's it. And then we are going to arrive at the IR theories of phi guy. Okay, just to show you how this second approach is done. Okay. You can choose other models. Yeah, you can choose other models or other interactions that is UV complete, and then you can try to integrate out to see how the IR theory is. Yeah. Okay. Right. So now the idea is to write down the IR theory for this guy phi. Okay. Right. And actually, the proper way to do this is to use the path integral. But okay, I just mentioned that one has to use the path integral to obtain the effective action for the light field phi. Okay, but in practice, I'm going to use just a 3-level like equation of motion to do that. Okay, so formally you have to write down the path integral. You have to formally, yeah, you have to write down e to the I is. Yeah. So this S effective is an effective action for the light field phi, okay, and whose mass is less than the mass of the heavy guy. Yeah. And this is given by the path integral. E to the I. Okay, so essentially you integrate out the heavy guy chi here. Okay, and we get the effective action for the light guy. Okay. Anyway, so the idea is that now we're just interested in the 3-level. Okay, 3-level. I mean, in the sense of the Feynman diagram. I hope you have. Okay, fine. Okay, then we just write down the IR theories. For example, just write down. So suppose that the IR theory or IR Lagrangian takes this form, okay? I will explain later. plus pi order 2. Okay, so what happened is that here we just write out the IR, the theory that the energy scale is less than the mass of the heavy guy. Okay, so this happens when the energy scale of your interest is less than the mass of the heavy guy. Okay, so you can just write down this action, the kinetic term for the light guy here with some coefficient in front, and then the mass term, and then the interaction term, and so on. And then we are going to do the matching condition from this IR theory with the UV theory here. Okay, because now we know that we know the UV completion. So here is just a top-down approach. Okay, and we can determine this Z and M's tilde here and lambda in terms of the UV parameters. Okay. So the idea is that starting from these UV theories, you can write down the equation motion of the heavy guy. Okay. So let me just take this Lagrangian value with respect to the heavy guy chi, and then get the equation motion of chi. Okay. At 3 level. So just write that equation of motion. Okay, it's like this, no? Yeah, well, it's very easy. And then you can you can inverse this operator to get chi, right? You can solve this equation motion. Essentially like this. Okay. And so in the effective field theory regime, where the energy scale you're interested in is less than the mass of the heavy guy here, you can just simply Taylor expand this 1 over box plus m square. Essentially, this box is like the energy squared. Okay, so you can just Taylor expand this factor to get the following. M then G sum M box. Okay. Yeah, so you see that the more you go in this series, the more is suppressed by E over M. Okay, so because we're now in the regime where E is less than M, so this term will be more and more suppressed when E is less than M. Okay, so this is more and more suppressed. More suppressed for E is less than M. I forgot to say, sorry. This M in some sense is like a EFT, is the cutoff of the EFT. So I forgot this terminology. If you want, M is the cutoff of the EFT. Cutoff of the EFT. But when we talk about cutoff, we have to be careful because the cutoff here is yeah, you can think of the mass of the heavy guy as well. But in other language, like from the QFT side, if you do the scattering amplitude things and then you do the unitarity bounds, then that unitarity bounds can be the cutoff of your EFT as well. Okay. In the case where you don't know about your UV completion, you do everything in the EFT and you compute the scattering amplitude and require to be unitary, and that is another cutoff. Okay. So we will discuss that later. But for simplicity, that this mass of the heavy guy is just your cutoff. Okay. Okay. Anyway, so the idea is that you have this solution for the heavy guy here from the question motion, and then what you have to do is you have to plug this back into the rule there, to the Lagrangian of the UV, to replace all the chi field here with phi here. Okay. Then what you get is the following. And by doing this procedure, solving question motion of the heavy guy, plug it back, correspond to integrating out the chi field at 3 level. Okay, you can go to the loop level if you want. Then you have to complete the loop diagrams and so on. Okay, and that is going to be like a high order in the coupling, like G square, whatever. But let me show this 3 level, and then we move on. Okay, we use that solution and plug it back to the UV Lagrangian. Okay, substitute back. Chi in terms of phi at 3 level using equation of motion. Chi equation of motion. And what we get is the following. Okay. Yeah, so basically, if you plug that back to the cubic term, do you remember that we were having G phi square, like we were having the cubic things like this, no? And if you plug that chi back here, you are going to generate the quartic vertex or quartic coupling for phi, like a self interaction for phi in the EFT regime. Okay. And then those derivative high order terms here, if you plug back to the, say, the mass term of the phi in the UV, then you're going to generate things like a derivative couplings for that. Okay, because it here, you see, it contains a derivative. And if you plug back, you get derivative. Something like this at order G squared. Okay, but actually when you talk about order G squared, one has to be careful because the order G squared can mix with the loop diagrams while this loop. Let me show you. So we have this interaction, no, like of chi phi squared, and if you want to describe the 4-point function, it's okay. Yeah, like some kind of phi 2 phi. Okay, like this. There's the scattering of the light field here, and then you can draw a diagram like this, no? This phi, chi here, and phi. This is at 3 level, but then you can go on to the loop level. I think. I hope I'm not. Let me check. Yeah, I think you can go to the loop. Yes. No, loop is no loop. It's like this. Okay, let me talk. It's like a box diagram. Box. But this is of order T. T to the 4th already, but okay. Phi, chi. But anyway, here we're just interested in the 3 level, and essentially, yeah, if you do this kind of matching, you can determine what z here, the m tilde and lambda here. Let me just write down. When you have this Lagrangian, you can do the matching with that, and then you can write down z as 1 because it's 1 here, and plus the order of G square, I think, if not mistaken. So essentially what it means that at 3 level, this kinetic matrix term is just one there for the light field. Okay, and those corrections coming from other diagrams, like loop diagrams, so on. Like for example, if you want to, because at 3 level it's just like this, no? Phi. I hope you guys at the end see, or maybe I read this. Okay. Okay. So the fact that you start from this, the propagator of phi, which is just the 3 level, which is 1 here. And then you can plus other corrections coming from the contribution from chi here. Okay. So basically you have this kind of diagram. Phi to v, like this. Phi, phi, phi. And this is of order g squared. But you see that this diagram contributes to this g square order. So that is a loop corrections. Okay. And what you have to do, if you want to know this correction, you have to go on and compute the loop diagram here. And you have to deal with perhaps some renormalization or regularization, because this is 1 over p squared, 1 over p squared. You integrate over d for x, so you get log divergence. Fine. And then you have to renormalize it basically, and then you get this t square orders. Okay. And for what else? M tilde here. Let me just write down M tilde. M tilde is basic. M squared. And of order t squared. Yeah. So for the mass term is more or less the same as the kinetic term. Okay. That order g square come from the loop corrections, but now you have lambda, which is the kind of the coupling for this circle interaction, and this lambda is basically at 3 level. You see that the lambda is g square over 8 m squared. Okay. Or well, here we normalize by 4 factorials, then it's going to be minus 3 g squared, g to the square, yes, divided by m squared. I hope I get it. Okay, and then plus the high order terms. And high order term here is of order, it's like this. So of order g 1, 2, 3, 4 is of order g to the 4, and that is a loop corrections. Okay. And this is at 3 level. This is 3 level for lambda, 3 level, 3 level. So in this sense, if you have this kind of diagrams at 3 level in the UV, so what you just did by plugging in the solution from equation motion back to the UV, it means you just integrated out this chi field here that present in the inside the diagram in the UV. Okay, so yeah, basically we just integrate out this guy, and then this guy chi will not appear as external legs of the theory. Okay, right, and this is going to be a loop. Corrections like this. Okay, chi. Okay. Whew. And essentially from the EFT point of view here, if you look at this IR Lagrangian, you can write down the vertex something like this. No? Yeah, and this lambda. And this lambda is the vertex, is a coupling in the EFT. And this lambda is given by the UV coupling g squared there from the UV physics. Okay, maybe let me pause here and then take questions.
So I just see that like from this Lagrangian, there is no 3-point vertex. Like, do you have any good reasons for that?
The 3-point vertex, you mean phi cube?
Yeah.
I think you don't get that when you plug at 3 level. When you plug in the equation motion, the solution of the equation motion from the UV of chi. There. But I think you can get something like this. You're asking this, no?
Yeah.
But at 3 level, you don't get. No, I don't think so. Phi chi. No, you don't get this.
But in general, like,
But you say 1, 2. No, it's okay. Yeah. No, yeah. Sorry.
but in general, like if you pick any UV Lagrangian, like why?
If you write out the EFT like this, without knowing the UV completion, of course you are allowed to write down phi cube, no problem. It's okay. But suppose you impose the C2 symmetry, like phi 2 minus phi symmetry, and that C2, phi cubic is going to be excluded by symmetries. But you can write down phi cube and phi 6, phi 100, whatever, and then you try to do this matching from the IR and the UV, and you just determine what is going. Yeah. From this, yeah, because chi here, exactly. So chi here is just is a function. If you remember, it's a function of phi squared. Chi is a function of phi square, and also here, even though you have a derivative, it's also acting on the phi square. So it's kind of even function in phi square. So you don't get the odd power of phi in the EFT. But using this procedure, yeah. I would say that it's coming from the construction of the UV. Do we take a break or not?
Okay.
Do we take a break? It's already
Okay. Take a break.
Yeah, take a break now. Do we take a break?
Mìnhต้องเริ่มเชื่อใหม่นะ
เอาสักเอาสัก10 minute break.
10-minute break. Okay.
ลืมเลยโทษทีไม่ฟังเลย
โ
Okay, let's start the next session now.
Thank thank you thank you thank you
พี่ง้วงมาที่ชวน
thank you ครับพี่ม้อง thank you มากขอบคุณมากครับพี่ม้อง
โซเดียมดีขึ้น
ดีขึ้นครับดี
ต้องไปคาเทียน
Okay, welcome back. So yeah, so far we have seen the how to derive the IR Lagrangian starting from the known UV completion, like in this example that we saw, the two few examples. And so let me just summarize what we have done so far and in terms of diagrams. Okay, so that maybe you will understand better. Okay. Okay. Yeah. So let me remind you that in the UV Lagrangian we have this interaction. In the UV we have this G. What the hell is that? G over 2 chi phi squared. Yeah. Okay. So in the UV Lagrangian we have this cubic interaction for chi, and for the kinetic term in the IR, suppose you interested in this kinetic term for the light field. So what you have to do is you have to compute this 2-point function of the light field. So diagrammatically, what happened is that at 3 level, this is equal to like this, no? And then plus the contributions coming from the heavy guy that I just wrote down. Okay. The loop of chi, G, okay. Like this, and so on. Okay. And actually, if you go on and compute these loop corrections, I think there is an exact formula for this. But okay, this is in the UV. Okay. Because you still have chi present in the diagrams, but in the IR, what happened is that you can just take this. This Z plays a role of some sort of blob here in the middles, and then two phi's has an external legs. Okay, so this is from the IR language. Okay, and if you go on, if you want, you can compute this loop diagram. Which maybe I don't have this. Fine. Okay. Anyway, this is 1 divided by Z p squared minus m squared. Okay. And also, if you want to, to write down this lambda in terms of the UV couplings. So lambda is like kind of a quartic coupling, so it's something like a 4-point function. If some of you don't know what the 4-point function is, just ask me later. Okay. So yeah, 4-point function of lambda of phi, it goes like so. At 3 level, it's just these. The first contribution coming from these diagrams, because in the UV you don't have lambda phi 4. You just start from this coupling, and this form, when you integrate out chi, you generate lambda phi 4 in the IR. Okay, and then plus corrections. In this case, it's a box diagrams, I think, like this. G, 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 G. Okay, and then there are 4 phi's as external legs, and then there are other diagrams like these. Let me just draw. It's very my bad habit to use fingers. I think it's a bad habit. Bad habit, very bad habit. Okay, here you have G here, G here, chi here. One chi, two phi's. Okay, one chi and two phi always. And this of order G to the 4. Yeah. Okay. And you can go on and compute this loop diagram. And in fact, this loop diagram is finite. There's no divergence because this like let me just do some estimate. Okay. So when you do when you have the loop diagram, you have to integrate over d4 p, and p is a momentum in the loop, and then for each line, for each internal line, you have 1 over p squared for the scalar field. Okay, this is phi, all are scalar field, so it's just 1 over p squared, so it's 1 over p squared to the 4. So this is going to be p to the 8. So overall, you have 1 over p to the 4. So this is finite. So this is a UV finite. You can compute this loop diagram exactly without doing any renormalization or regularization and so on. But some diagram maybe contains some divergence, but it's okay. And so this is in terms of the UV language. So you still have the coupling G here, but from the IR point of view, that you have lambda 5 there, you have basically this blob, something like this in lambda. So all the informations of chi that in the UV has been encoded in terms of the EFT parameters, okay, in this lambda. Okay, and in practice, when you suppose that you are interested in the scale that below that's below the mass of the heavy guy here, suppose you are interested in physics at this scale, and you want to compute the scattering of phi, you can just simply use this theory, the IR theory, and that's it. Okay. All those information of the UV physics has been integrated out and put inside these EFT parameters. Okay. Okay, I hope. And let me show you other example of the EFT that we know so far, like the one of the Euler-Heisenberg Lagrangian. Okay, so in that case, you start from the QED Lagrangian. I assume you know QED. Fine. So QED is a theory of it's a theory of the electron fermion and the gate and U1 gate field. Okay, and it's renormalizable that we know. QED. So you can write down the Lagrangian of the QED. Which is like you have the kinetic term for the gauge field, and F mu nu is the d mu A. Like this. And then apart from this, you're going to write down the Dirac Lagrangian for the electron. Mu. Okay, but this should be covalent derivative. Well, mu. Okay, this is just a partial derivative, and here there is an interaction between electron and the gate field, 2 electron, and this mu. Okay, I hope I get the sign correct, but yeah. Well, there's no I. Yeah, because there's I here. Okay. Anyway, so this Lagrangian, of course, we know that it's invariant under the gauge transformation. Sure. the mu lambda like this, where lambda is just a function of x. Of course, we take this QED as a UV completion, and then we are going to integrate out the electron. Okay, integrate out the electron. And to get the IR theory for just a photon. Okay, to obtain the IR theory for the photon. And the mass of the electron will play the role of the cutoff of this EFT. Okay, with ME being the cutoff of the EFT. Okay, so there are two ways. Actually, since we know the UV completion, you can just go on and then integrate out the electron. But the thing is that in this case, there are loop corrections. Okay, so there are loop corrections, like you have to do something like this of this sort. You have this is gamma, so gamma should be present outside the diagrams. Okay, and then you have to integrate out the electron like this box diagram here. Mu, let me use gamma. Gamma is photon. Okay, and then for each vertex it contains E, right? The electric charge here, which is the coupling. And then you see that this loop diagram is of order e to the fourth. And e to the fourth is like alpha squared. Alpha is 1 over 100. No, it's a fine structure constant thing. Okay, this is like alpha squared, which is 1 over 137. I think. Anyway, so this means that when we are going to write down the EFT for this photon, it's going to be this term, as a leading order, plus the high order terms in this case, it's going to be a to the fourth. Okay, but you see that in this f squared, it doesn't contain a to the fourth. It contains only a squared. But then you have to add more terms here. Okay, so let me just write down. And this is the so-called the Euler-Heisenberg Lagrangian. Okay. So the IR. So the IR Lagrangian is going to be the first term as usual. It's a kinetic term for the photon, right? And then the next term is going to be the high order terms in mu. That is like some kind of f to the fourth. Okay, so let me just simply write down as a times f mu nu squared. So this term contains 4 power of a mu. Okay, contains 4 power of a mu. So that means in terms of the EFT language, it allows you to have the contact interaction between photons. You see that from the UV point of view, it doesn't allow you to have the contact interaction between photons. Okay, you see that there's no f to the 4 here. But from the EFT point of view, you can write down this kind of thing. Okay, so mu, and mu. Okay, but this is like proportional to A, which is the coupling here. Okay, and the dimension of A is what? Here it has 4 dimensions and 4 squared 8. So A has to be dimension minus 4 in energy. Okay, so A has to be dimension minus 4. But not only these, you could have other terms as well, like this term, f mu nu tilde square. Okay, and f mu nu tilde is a dual of f mu nu epsilon rho sigma F. Maybe there's 1/4 factorial, but fine. Rho sigma. Yeah. But yeah, you know, if you just write down, yeah, you can ask the question why you don't write down F mu nu tilde, and that term is the total derivative, so we don't care about that. And also, you know that this F mu nu, F tilde breaks parity because it's like a E times B, the magnetic field times the electric field. Okay, but this term is the total derivative, so you can just forget about it. Okay, and we can just write down this term and then do the matching between this IR theory and the EFT and the UV theories, and what you get is the following. If you do the matching at the, if you do the matching at the energy around the electron mass, you get this coupling in terms of the fine structure constant as alpha squared divided by 90 me to the 4th. Okay, so this coupling A here goes like 1/, the mass of the electron to the 4th. Okay, this guy alpha doesn't have dimension, and B essentially is 7 alpha squared times divided by 360 me to the 4. This is from the matching between this theory and that UV completion. But in this case, you have to compute this that loop diagrams. Okay, but there are other channels. This is like a S channel, whatever. The S channel, but you have to sum other like a T channel or U channel as well. You have to sum all the diagrams that contribute to this 4-point function of gamma. Okay, and then you get this result. And but suppose you don't know about QED. Okay, suppose you don't know about this Lagrangian. You can also write down your EFT of photon like this, and you could add other terms as well. Okay, and then you can determine or put the bounds on this coupling A and B using the observations. Like you do some the dipole measurement, and then you put a bound on this A and B. And this is an observational bounds. Okay, but here, since we know the UV completion, then we can do the matching even better. But in the case of gravity, most of the time, the fact that we don't know about the UV completion of gravity, then most of the time we need to rely on the observational bounds that I will show you maybe in the last lectures. Okay, let me go on. Okay. So any equations that I will move to the second point, to the second lecture, second topics. So far we have learned about some terminology in the EFT, like the cutoff, derivative expansion or field expansion, that you have to organize term using the derivative expansion, and then we know that if you start from some UV completion, the non-UV completion, you can integrate out the heavy guys to obtain the IR theories, and you can use this IR theory to calculate the physical observables like scattering amplitude and those things. Okay, actually, from this IR point of view, we can discuss like the behavior of the scattering amplitude, how it goes as an energy. Okay, so there's another topic that gonna be interesting. Suppose that let me just mention this. If you take this theory and then you go on and compute the scattering of A mu like this, so 2 A mu's scattering and then goes to A mu, and this amplitude it grows. It's gonna be as a increasing function as an energy. So this amplitude. Let's say M4 here, it grows with energy. Grows with energy. You can try. You can try and then compute the scattering amplitude, and you see that this grows with energy. And let me mention that the fact that this guy grows with energy, then at some point you can imagine that when the energy reaches some certain energy scale, you're gonna break unitarity bounds. Okay, because unitarity means that you have a conservation of probability, and it places the bound on the scattering amplitude, and it simply means that yeah, there is a when this M4 here is of order unity, roughly speaking, you reach the unitarity cutoff. Unitarity cutoff. Okay. Let me say this is lambda unitary. Okay. And this lambda unitary could be usually is larger than m electron. Usually is larger than the mass of the electron. Okay. Like yeah. Let me just draw here. Oh. So you have a mass of the electron as a cutoff. Yeah, sure, fine. But here, ME. And we are saying that we can use Euler-Heisenberg-Lagrangian here, right, below the ME. But then suppose you do the scattering amplitude at this low energy physics, low energy scale, and then you have the unitarity cutoff could be above the mass of the electrons here. And this unitarity cutoff, it means that your calculation here remains weakly coupled. Okay, so that means the perturbation theory works up to this unitarity cutoff. But you see that the fact that you reach is ME before, then the EFT breaks down at this point. Okay, before you reach the unitarity cutoff. So this means that when E is less than lambda cutoff, lambda unitary, it means that the theory remains weakly coupled. It is very important because the fact that theory remains weakly coupled, it means you can do the calculation by hand. Otherwise, forget about your Feynman diagram. Remains weakly coupled. Otherwise, you have to use the lattice like QCD and whatever. But, yeah, weakly coupled. Okay. Yeah. Yeah, so what I'm trying to say that suppose you don't know about this UV completion, and then you take that EFT as it is, and then you do the computation up to this unitarity cutoff, and the calculation remains valid up to this scale. But since we know this UV completion, then yeah, we know that well, when the energy scale reaches the mass of the electron, then you have to take out the contributions coming from this electron. Yep, that's very.
I want to ask about unitarity cutoff.
Yeah.
I think you means that if we beyond that cutoff, that means something like probability current is something like diverged, something like that. Or is it,
so what it means by when the energy scale is compatible to the unitarity cutoff, I think it means that your perturbative calculation breaks down. Yeah, so you cannot do the perturbation theory around the free solution. So perhaps you have to change the starting point. You have to find the non-trivial solution and then do another perturbation theory around the non-trivial solution. Yeah, that's what I mean.
How you get this cutoff?
So yeah, first thing, the formal way is to use the so-called partial wave decomposition. So you can write down your scattering amplitude as a basis of the YLM, blah, and then there's some coefficient in front of YLM, and then you require that this coefficient, you require the unitarity, means this should be less than unity, probably speak schematically, and then the fact that this 4-point function or 4-point amplitude depends on energy, and then you require this to be less than unity, then you see that when the energy scale that this guy reaches unity, roughly speaking. Yeah.
Another question, because now we integrate our precise, right?
Yep.
It's fermion.
Mm-hmm.
So let's please talk about how we integrate our in particle formula, because now it's fermion.
Yeah. Oof, this fermion.
Other than Strelfield. Yeah, talk a little bit.
Yeah, sure. In this case, you just have to write down this the path integral formula for the mu. So it's effective action for mu in the IR, and then you have to integrate over the fermion. But then fermion, you have to sidebar as well, I think, because fermion is a complex thing. So it's that psi and psi bar is a yeah, and then you integrate these. It's a QD, mu, and then psi. And then one way to integrate these is to do the semi-classical approximation. So that means you just write down these as a psi classical plus some delta psi here. And then you plug these back, then well, there's a h bar here. And semi-classical approximation means that you send h bar to 0. And then you can approximate this path integral. As a leading order is, of course, is e to the is evaluated on the classical path. Okay? But fermion, yeah, you can write, it's a Dirac equation, no? No. And some mu. But you see, when you vary this action with respect to psi, then you get some sort of psi bar times mu. You cannot solely integrate out or solve this psi e in terms solely in terms of mu. So it kind of still coupled. So in this case, that's why at leading order in the EFT, you start with the loop corrections. Okay. Anyway, so let me just finish. Here it's a psi evaluated classical path, and then you have corrections. So it's gonna now it's gonna be the path integral of this delta phi, right? And then okay, delta phi, and then then you have to expand these, and then you get the delta phi square, and then it becomes Gaussian integral, and then this becomes determinant of the second variation of action. Okay, it's fine. I think you can idea. You don't have. Well, yes, and since it's a fermion, then yeah.
This recall me that that equation, yeah, it's quite something like three-level matching, something that we can substitute psi.
No, but
from this equation.
But we have to be careful because in the case of fermion, you see that this source term also depends on this psi e and mu. So you cannot solve psi e solely in terms of mu only. In the case of two field models, I particularly choose the fact that you can solve chi solely in terms of phi.
Yeah.
That's easy. But in this case, yeah, you cannot. How can you? No. Yeah. No. Yes. So you have to use the path integral, and then basically you have to do computer loop diagrams and to do the matching with this. Yeah. And the fermion here is proportional to the determinant, but for the scalar field, it's 1 over determinant. But fine. Yes, and usually this classical. Now let me. Usually this classical trajectory is just a free fermion. No? You forget about this coupling, and then you have the classical path. But when I was mentioning about non-trivial saddle point, it means that suppose you take the full classical equation, and then suppose you can solve this differential equation. Whether numerically or analytically, whatever, and then you find the new saddle point here, and then you could do another perturbative expansion around the new saddle point. Okay, but it could be complex, huh? But right. Thank you for the question. When do we have lunch? When do we have lunch? When do we have lunch?
You can stop.
I can find it out. ทั้งวันเลย Okay. So my second lecture is about the theory of goldstone, right? That I mentioned. Okay, so the theory of goldstone. So here we are going to learn about how to break the symmetry, because so far we have not discussed much about symmetries. So in this lecture we are going to incorporate how we break the symmetry and what the consequence of that. Okay. Okay. So let me. This is okay. Okay. So let me just start with this, and then we go have lunch. Let me start with the spontaneous symmetry breaking. Spontaneous symmetry breaking. Okay. So when you talk about the symmetry breaking, there are two kinds of breaking. One is the explicit breaking, and the other is the spontaneous breaking. And here we are talking about the spontaneous breaking. Okay, and spontaneous breaking, it means that the background of the field that you are interested in acquires some non-trivial vacuum expectation value. Okay, so some field, like a scalar field that in our scalar tensor theory, some fields acquire non-trivial vacuum expectation value. Expectation value. Okay. In terms of the operator language, it means that this, let's say that you have a phi 0, which is the background for this sum field. You choose this guy to have a non-trivial background or non-trivial vacuum expectation value, and when some symmetry is broken, it means that that corresponding charge or corresponding conserved charge acting on this operator, acting on the vacuum or the background is non-zero. Okay, so this means that this vacuum on the background carries the non-trivial charge. Okay, so it's not non-zero. So this guy carries non-trivial charge. And we say that the corresponding symmetry to this charge has been broken, has been spontaneously broken. Non-trivial charge. Okay, and the breaking of symmetry could be internal symmetries, the one of the gauge group, like a standard model, SU2, class U1, or it could be the space-time symmetry, like a Lorentz symmetry as well. But the counting of the number of the massless degree of freedom is different between the two cases. Okay, so let us first start with the spontaneous symmetry breaking of the internal symmetries, like a standard model gauge group. But we don't start the SU2 cos U1 since it's that gonna take me another 5 hours. But let me start the U1 complex scalar field. It's very easy, but we learn a lot from that. Okay. But maybe I should say something before. Yeah. Maybe I should say something before I go to the example of the U1. So suppose that you start from the symmetry group. G is the full symmetry of the Hamiltonian. Of the Hamiltonian. And then what happened is that you break the fact that you have some non-trivial background. Let's say this phi 0 or this guy is a non-trivial background. Non-trivial background or web. This web. Then this symmetry group G has been broken down to H, and this is unbroken symmetry. Unbroken symmetry group. Okay, and the number of broken generator is equal to the dimension of this guy minus this guy. Okay. The number of broken generator. Generator. You know what generator is? Fine, whatever. Dimension of G minus dimension of H. Okay. Actually, in the field theory language, when we say some symmetry has been broken, we say that that symmetry is non-linearly realized. Okay, so when symmetry has been broken, we say that has been broken. This is equal to the fact that this symmetry is non-linearly realized. Okay, non-linearly realized. So it's not like this symmetry is gone or disappears, but it's there, it's still there, but it's not linearly realized. Okay. Well, of course, if you go to the full Hamiltonian, it's still the full symmetry is still there, but now we're talking about around the non-trivial background, and this means that this background is non-linearly realized these broken symmetries. Okay. And then there is a theorem that corresponding to this is a so-called Goldstone theorem. Okay, the Goldstone theorem say that well, I will finish the Goldstone and then go for lunch. Okay. Goldstone theorem. Yeah, sure, sure.
I still don't understand what you mean by non-linearly.
Realize maybe in the example I will show you how to actually chip symmetry is a non-linearly realized, but we will go to some example to see this better. But yeah, or the translation also did non-linearly realized translation, like x mu goes to x mu plus a mu, and this is kind of non-linear transformation in the sense. But rotation x mu, like you go to lambda mu nu x mu. This Lorentz transformation, like a rotation SO13, is a linear transformation. Okay, but we will go to that. Don't worry. Yes. Let me finish this with the Goldstone theorem, and then I stop. Okay, I stop. Because whenever you break symmetries, there is a corresponding massless degree of freedom as outcome. Okay, so let me just write down the Goldstone theorem. Goldstone theorem, and so I'm not going to prove this theorem. You can look at the Weinberg's book and then do the proof. I'm not going to prove this. Okay, so the theorem is said that that there exists the massless particles, the massless degree of freedom, or massless particles. Okay, and the number of these massless particles is equal to the number of broken generators. Okay, or it's equal to the number of symmetry you have spontaneously broken. Okay, equal to the number of broken generator. But there is a caveat for this theorem that it applies only to internal symmetries. Okay, it applies only for internal symmetry, like U1, SU2, whatever. But if you break, for example, translation, which is not the internal symmetry, translation is a space-time symmetry, then the counting of the massless particle and the broken generator are not the same, because you have the so-called additional, the inverse Higgs constraint. But okay, we will not talk about that anyway. But yeah, so for example, like for the internal symmetry, you have U1 or SU2 and so on. And yeah, so maybe in after lunch I will show you how to break U1 symmetry and to get the massless particle. And this massless particle is the so-called Goldstone boson. And we are going to see the Lagrangian of the Goldstone boson. Goldstone. Actually, it should be Nambu Goldstone boson, but fine. It's a massless. Okay, and then apart from this Goldstone boson, we also have the Higgs, which is like a heavy particles for these. Yeah, and we will see. Yeah, after lunch. Okay, I think that's we go for lunch. So the Euler-Heisenberg Lagrangian is just the IR. So the Lagrangian only for the photon when the energy scale is less than the mass of the electron. So when E is less than ME, then you can write down this Euler-Heisenberg Lagrangian that contains the self-interaction of photon. Normally you don't have this self-interaction in the QED, you know, but in the Euler-Heisenberg you have a mu to the 4, a mu to the 8, and so on. So these are the kind of EFT of QED. There's Euler-Heisenberg.
So is it part of the nonlinear electrodynamics?
Oh yeah, good question. So in the case of in the Euler-Heisenberg you can generate exactly the nonlinear coupling of a mu, and yes, the answer is yes.
But what about something that the estimate of
Well,
something?
as I remember, the unitary cutoff of the QED is a Landau pole, which is super high energy scale. Is like
Like the week, very near that.
I think it's even higher than in Planck, the Landau pole. Yeah, if I remember correctly, let me just go to. I think the Landau pole is at
30 something. Yeah, maybe later.
yeah. It's the Landau pole is around 10 to the 200 GeV, even more. So
Wow.
no, this makes sense because I mean, if you go up in high energy, you are going to reach the electroweak scale, the scale of gravity, and so on. So this means QED is not the complete theory anyway. So yeah. So even though it remains really coupled until Landau pole, but as you go up, you reach top quark, Higgs, and other things, and you have to take those into account. So QED is not the complete in this sense, even though it's remain really coupled all the way. Yeah.